Hello, my name is Madeline Boutwell. This is Colin Pagel, Alex Rios, Leah Jeffcoat, and Brittany Patton. We are all kinesiology majors at Texas Women's University, and we are Team Good Vibrations. To recap what our fall semester team did, they decided to tackle the issue of shoulder injuries in astronauts, specifically the shoulder injuries that are obtained in extravehicular activity training in the Neutral Buoyancy Lab. They created a device that sends vibrational feedback to the astronaut when their shoulder has reached an unsafe range of motion. Looking at a report done by NASA's Tiger team in 2003, we can see the top causes of shoulder injury during extravehicular activity training. Last semester, they created a device to warn astronauts when they are falling into the second cause of injury, HUT-related injury. This injury is called impingement. The hard upper torso unit of the spacesuit, or HUT, does not allow the clavicle to move as it is designed to during shoulder flexion or abduction, which causes stress and tearing to the muscles underneath. They created a device that uses flex sensors and vibration motors to warn the astronaut when they have reached an unsafe range of motion. This semester, we continued development on their design. We plan to expand the device into an athletic t-shirt that can be worn underneath the extravehicular mobility unit. We also expanded the device to send separate warnings for each shoulder. We updated the specs of the device so that it can accommodate a 6-hour EVA training. And lastly, we added a sensor to warn the astronaut when they have been in an inverted position for too long. This will allow our device to warn for the top 2 causes of shoulder injury during EVA training.
We continue to select Arduino as our coding platform this semester. The program is simple and allowed us to use smaller microcontrollers that would fit the product in a more comfortable fashion for the user. The Circuit Playground Blue Fruit became the microcontroller for us to use this semester. This board is only a few millimeters thick and becomes virtually unnoticeable to the user. The Circuit Playground Blue Fruit can be powered by standard AAA battery packs or lithium-ion polymer batteries similar to what we use this semester. These batteries are rechargeable via USB cable, and the Blue Fruit board also unlocked Bluetooth Low Energy capabilities, which we programmed to live stream sensor data from testing directly to our phones and computers. The built-in 3-axis accelerometer was put to work this semester. The board can now trigger the motor driver to notify the user they have been inverted for too long and need to readjust their positioning in order to avoid injury. The system would be nothing without the flex sensors, of course. As these sensors bend, the internal resistance changes, which the board can then read. When the sensors worn over the user's deltoids are bent from abduction or flexion, the program runs the haptic motor driver. This reliable driver can control LRA or ERM motors depending on energy and force requirements. The information is transferred via I2C communication, and the driver can be programmed to vibrate through different effects, frequencies, and strengths. The user will be most familiar with the eccentric rotating mass motor discs. The haptic feedback received is similar to a cell phone vibrating in your pocket. These centimeter-wide discs can handle the wide range of power, speed, and frequencies that the motor driver delivers to it.
As a team, we decided an athletic compression-based layer would be our best option to hold our components. We're using the Under Armour Cold Gear, which allows for multiple uses and comfortability for long hours. It will allow the astronaut to maintain full range of motion during training. The garment is fitted to the body, absorbs body moisture, and available in different sizes. Since the Under Armour is fitted, it allows the flex sensors to be flush against the body, which will allow more accurate readings. On the front of the shirt, there will be one flex sensor for each shoulder. The back of the shirt will contain most of the components. There will be 3 Circuit Playground Blue Fruits and 3 haptic motor drivers. Each of the haptic motor drivers are connected to an ERM vibration mini motor disc. An additional 2 flex sensors are included on the shoulders. All these components will have their own compartment in the shirt. For the SolidWorks design, I began by creating a replica of the HUT. I then created a fitted compression shirt to replicate the Under Armour Cold Gear. Lastly, I created each component used in our design and placed them on the shirt in SolidWorks. This gives us a digital visual of how the device will look under a HUT.
Final steps of our programming process required some preliminary testing to ensure that the vibration motors alarmed the user when flexing or abducting the shoulder beyond 90 degrees. With a goniometer, it was possible to measure the subject's angles of abduction and flexion in 5-degree increments, while noting the tension of the flex sensors at each measurement. Furthermore, we were able to program the haptic motor driver to react to the corresponding degree of our choice. Our reasoning for titling 90 plus degrees as the danger range was derived from the concept of the painful arc, which is from degrees 60 to 120 of the abducted arm. Excessive movement within the painful arc prompts impingement of rotator cuff muscles and ligaments, especially with additional weight or pressure, similar to something the HUT would initiate. Our main goals during testing were to verify that the device alarmed the user with tactile feedback at the correct tension of the flex sensors, like we programmed it to, and secondly, to ensure that our device did not cause additional harm to the user through pressure or discomfort or even restriction of range of motion, but instead proved to be effective when training with frequent overhead tasks.
As you can see here on the right, the participant is wearing our garment. The screen on the left shows the resistance being picked up by the flex sensor. As the participant abducts her arm, the resistance increases. When the participant has reached 90 degrees, the vibrational motor will alert her that she is in a potentially harmful position. That thumbs up means she feels the vibration. And here you can see that again as the participant is flexing her shoulder. Here you can see the range of motion in the shoulder graphed against the resistance picked up by the flex sensor. With shoulder abduction, resistance increases in both flex sensors as range of motion increases. But with shoulder flexion, the anterior flex sensor increases while the lateral sensor stays fairly steady. When the lateral flex sensor picks up a resistance greater than 30 kiloohms, or when the anterior flex sensor picks up a resistance of greater than 75 kiloohms, the vibration motor runs. Lastly, here's the device outside the garment. You can see that when the flex sensor has picked up the programmed resistance, the motor begins to vibrate.
As was the case with every team this semester, the unexpected pandemic that unleashed caused some setbacks to our project. To aid in the testing of our device, we had collaborated with the Department of Visual Arts at TWU to build a replica of the hut worn by astronauts during EVA training in the Neutral Buoyancy Lab. We used the EMU Shoulder Injury Tiger Team report to determine the sizing of the hut. Our replica was going to be made out of a thickened epoxy to give weight with an outer layer of fiberglass. Due to the shutting down of our campus, we were unable to finish this project. We had planned to use this to run the testing protocol derived from the research article, Human-Space Interaction, Understanding Astronaut Shoulder Injury by Alexandra Marie Hilbery. We had also planned to complete underwater tests of the shirt in the TWU natatorium. This was to simulate effects of EVA training in the Neutral Buoyancy Lab to see how the device would fare in that environment. The last test that we were unable to complete due to COVID-19 was a 6-hour test of the device. We chose 6 hours because it's the amount of time an underwater session typically lasts. We plan to run a testing protocol that involved movements done at the shoulder joint every 30 minutes. This test was to check the reliability of the sensors and battery, as well as the comfortability of the shirt and whether or not it hindered movement after a prolonged period of time.
In the future, we would like to see how this garment could be advanced. We would like to see how it could be adjusted to different joints of the body, including the hip. We would also like to add a microcomputer to the garment to collect and analyze data to see how often the astronauts are placing themselves in a position that is likely to lead to injury. And lastly, we would like to see how this garment can be customized to different body dimensions and preferences of each astronaut. In conclusion, shoulder injury is very prevalent in EVA training. We have created a device that astronauts can wear during their training to warn them when they are likely to be injured. Our hope is that this garment will allow astronauts to develop safe habits in their EMU, which will reduce injury both in the Neutral Buoyancy Lab and in space. We would like to give a big thanks to our faculty advisor, Dr. Rhett Rigby, our NASA mentors, George Salazar and Dr. Reyna, as well as Nick Levine, Dr. Gardner, Dr. Dragoo, and Dr. Parsons, who helped us tremendously on this project. And of course, we would like to thank the Texas Space Grant Consortium for this amazing opportunity. Thank you.